Alright, welcome back. It's finally time to talk about the command pattern. So command pattern is one of the patterns mentioned in this book, Head First Design Patterns. So let's start off by just reading the definition. The command pattern encapsulates a request as an object, thereby letting you parameterize other objects with different requests, queue or log requests, and support undoable operations. Let's try and figure out what they mean. So they're saying the command pattern encapsulates a request. Okay, so you've got an object and somebody sends a request to that object for something or to do something. And the point here is that that request, right? We have an object, somebody sends it a request. That request is what we're trying to encapsulate. So we're not about to encapsulate the receiver, the object receiving the request, and we're not about to encapsulate the object sending the request. We're about to encapsulate the actual request going between these two. So I don't know about you, but that actually sounds kind of interesting. And that should resonate with the name of the pattern. If you think about it, the name of the pattern is command pattern. So we're about to encapsulate a command. We're not about to encapsulate somebody receiving a command, nor somebody sending a command, but rather the actual command itself. Okay, next portion. Thereby letting you parameterize other objects with different requests, queue or log requests. What does that mean? So I think they mean that we can then take a bunch of these encapsulated commands and compose them into some kind of context. So again, we have the receiver and we have the sender, and we encapsulate the command into some kind of object. And if you have multiple commands as objects, you can suddenly pass these objects around. You can suddenly pass these commands around. And I think that's what they're referring to here. So they're saying we can parameterize other objects with these command objects. So you can now have things that are sets of commands. So you can have a list of commands that you're about to execute, or you can have a collection of commands that you execute when you press different buttons, and this is kind of what we'll talk about later. And when they talk about queue here, I assume that then they mean this thing about a list. So you take a bunch of commands and you put them in a list, and then you invoke the commands one by one by one by one, right? So then you have a queue of commands that you execute. Or we haven't talked about composite pattern yet, but with composite pattern, you could even make like a batch command. So you could have a command that contains multiple commands, such that when you execute this sort of batch command or this macro command, that macro command simply executes a bunch of different smaller commands. So you have many commands that's owned by a larger macro command. And when you say execute on that macro command executes all of the smaller commands. But we're getting totally ahead of ourselves. The last portion of this definition was and support undoable operations. So if you think about it, if you have a command that does something, the inverse of that command, the anti-thing of that command is an undo, right? So if I say I have a command that adds 1, then the inverse of that has to be that the undo definition of that command is that you subtract 1. So if I have then a command that does something, and it also supports an undo, which is the inverse of itself, then I can very simply call the command and then undo the operation by calling undo on that command, right? I added 1 and then I subtract back. And if you have a bunch of different commands that have encapsulated different actions and all of them follow this logic, that all of them have these undo operations, then it's very simple to implement very complex undo operations, because all of the different actions, all of the different commands are responsible for undoing themselves. So even if you have a queue of actions, even if you have a queue of commands that you execute in series, you can then undo backwards, because if you undo them in the opposite order of the order in which you executed them, then you would end up at the start, right? So you have this series of commands, you have this list of commands that you're executing one by one by one by one. So like, let's think about math, right? Let's say that you have something which is like, okay, add 1, add 10, add 20, add 40, etc. And then you have undo versions of that, right? So every command has its own implementation of what it means to undo itself. So then it would be like subtract 40, subtract 30. I can't remember what I said about the other numbers, but like the inverse of that. But again, we're getting super ahead of ourselves. So let's stop here and let's dig into it, and then let's get back to these points. Now, If you're new to the channel or playlist, I just want to say that what we're doing in this playlist is that we're walking through all of the patterns in this book, head first design patterns, one by one by one by one. So if you're not already subscribed, now is a super good time to subscribe so that you won't miss the next pattern. Beyond that, this book, Head First, is a super good book if you're new to design patterns. So I highly recommend that you get it if you're studying design patterns. It has tons of images and silly examples and all of that. So it's not just like a dictionary, it actually tries to help you understand these patterns by giving you some context and rationale and like narrative. So highly recommend it. However, if you're not new to design patterns and you're more looking for like a reference book or like a dictionary of design patterns, I wouldn't recommend this book. Instead, I'd recommend this book, Design Patterns, Elements of Reusable Object-Oriented Software by Gang of Four. So this is like the de facto classic design patterns book. So if nothing else, this is something that's really good to put on your bookshelf for the future so you can go back and refer to this. Super good, I use this as a reference book. But if you're like me, I mean, just get both. But now, let's get into the command pattern. So if you've seen my other videos, you know that I've got some varying opinions about the examples from this book. Some of them are superb and some of them not so much. The example for command pattern I actually find extremely suitable and kind of logical. I mean, it kind of makes sense. And actually, I mean, I don't know when this book was written, like probably more than a few years ago, but I would actually say that this example kind of becomes more and more relevant. Maybe the pictures are a bit outdated, but the example is super relevant. So what they talk about is they talk about smart homes. They talk about home automation. So think about like you have Wi-Fi connected light bulbs and a Wi-Fi connected coffee machine and your thermostat is connected and like all of this stuff, right? More and more of the appliances in your home become smart devices that you can control from your smartphone or from some other device. Essentially, you put them all on your network and you can control them remotely either from your home via your own Wi-Fi or via the internet back to your home. So they've got this example of this remote control that looks, I mean, completely like 1990s, 1980s, I don't know, like super old, right? But anyways, I mean, let's follow the same example, but let's try to modernize. So in my home, I've got Philips Hue lights. You're probably already familiar with Philips Hue or some equivalent, but it's essentially Wi-Fi connected light bulbs. Or I don't know if it's Wi-Fi, but they connect to your router somehow. So one of the things I've got in my home is this controller. And usually it's on a wall, but I figured this makes a very good example. So if you check this out, you can see that we've got 4 different buttons on this. So we've got on, dim up, dim down, and turn off. The thing about this controller is that via the Philips Hue app, I program these different buttons to be connected to different lights. So let me just show you how it works. So most of the lights are on now, but I'm not sure this is going to be visible on camera, but if I press off, on, yeah, that's hardly visible. Let me do this, wait. Off, on, dim down, I think you get the point. So here's the scenario, slightly adapted from the book. Let's say you're running a company and you are tasked with building the smartphone app that users, like me, use to program this device. In other words, when I press on here, I might want a different thing to happen than when you press on your device. By the way, let me just mention that Philips Hue, totally awesome. This is not at all a paid endorsement, but if you've got the money to spend, it's totally awesome. But that's completely out of context for this video, so let's move on. You can think about it this way, for example. So I have lots of different Philips Hue bulbs in my home, and some of them are light strips, some of them are in different rooms, some of them have color, some of them don't have color. And if I buy multiple of these controllers and then put them in different rooms, one way of thinking about this would be that I would want the on button to turn on lights per the room that they're in. Turn on the lights of the room in which this particular control is in. But it could also be that I have like 2 sections in one room, so I would want to have one controller for half of the room and another controller for the other half of the room. Or now I'm going beyond what's actually supported by this particular control, but I'm just thinking like if we would design this application from scratch, these kind of things would probably make sense. Or potentially I would want it this way. I would want like I have 2 controllers. The on button of one controller controls half of the room. The on button of the other controller controls the other half of the room. But the off button turns off the lights in the whole room. Right? That scenario also makes a lot of sense, right? It's like wherever you are in the room, you want to be able to turn off the lights because you're leaving, but there are two physical portions and you want to be able to control them separately. Let's say like one is the office part and one is the leisure part or something like that. So when you're building this kind of application, the word dependency injection should really come to mind, right? Because we're saying that the actions of any particular button here can't be hard-coded into the class representing this control. Or I should start to say invoker, because this is the terminology that they're using in the book. So this is the invoker. It invokes commands, right? So this invoker, we can't hard-code commands onto these particular buttons because we want users to be able to design that themselves. So this is why we want to have the notion of a command. We want to have a set of commands, right? Let's say one command is turn a particular light on, and then you can attach a light to an instance of that turn light on command, and then you put that command on this particular location. Maybe another command is turn room on, right? Turn all lights in room on, and then to that command you pass a room ID, and then you attach that command to a particular button. So on and so forth for these other buttons. So this would be a dim up command, for example, and this would be like a turn off command, where this turn off command is either maybe a turn off all lights in room command, or turn off collection of lights, or turn off light. For example, right? We're just thinking about a bunch of different applications. Potentially, I mean, you have to try to think a bit outside the box. Like maybe my example is too simple, because since all of this is focused on lights, maybe you would have a single on command and a single off command, where the single on command would take an array of lights, for example, where if that array only contains a single light, well, then it's a single light, turn on a single light command. And if it contains multiple lights, well, then it's a multiple light command. That would kind of make sense architecturally, but if you think about it, if this controller is not only a Philips Hue controller, but like a universal controller, a smart home controller, where I can attach lights from different manufacturers. I think there's another brand called Lifex or Lifex or something like that. So you would be able to connect those lights onto this controller as well. Or maybe you have a Nest thermostat, or like, or maybe some is it called Wemo, the on and off switches. Anyways, like you have a bunch of other smart things in your home, and you want to be able to control those with the same controller. And if you think about it that way, you can see that like the same architecture can actually be used regardless of which thing I'm plugging in, right? Because let's think about it. The one thing that's the same across all of the things that we're talking about is that we want to press a button, want to send a command to a particular device that does a particular thing. And this whole notion about attaching the command to the button and then sending the command whenever we press the button, that's completely the same thing across the board. We construct the command, we inject that command into the invoker, and whenever the invoker is pressed, then we send that command off, or we execute that command, and that command might do something to something else. And in the book they call this something else, they call it a receiver. So the light here, that's a receiver. So invoker, we attach a command to the invoker, and the command, when it's executed, actually does something to a receiver. Probably you can realize how massively powerful this is. You can have tons of invokers that just couple to command. Any command can do anything it wants to any particular receiver it wants. And if you're sharing interfaces with receivers, maybe you could even use the same receiver for multiple commands, but that's a different story. So let's now actually look at some UML. Okay, so here's what we've got. We've got, as we were saying before, an invoker. This is, as discussed before, this thing, the remote control. And the invoker has, let me put 0 to many, command. And this is an interface, so let me put I here to say I command. So the invoker has 0 to many commands, but not concrete commands. It couples to the interface I command. The interface I command then, of course, has a number of implementations, and these we call command. And any particular command acts upon, i.e. has, a receiver. And the receiver is the lamp. So the invoker, the control, the remote control, is loaded with, its buttons are loaded with commands, I commands. We define these as I commands, and Because the I command is an interface, it needs to be implemented by something, and it's implemented by any particular concrete command. And this command could be like a turn on light command, or turn on all lights in room command, or set color of light command. And that command acts upon some particular receiver. In this case, since we're talking about lights, a receiver would be something like this light. So in the head first book, they've got another portion which is the client, which is essentially the thing using this pattern. But I think this is really the main portion of the pattern, so let's stick to this portion and we'll talk about how to use it. So let's now add the methods as well. So the methods they add is that the invoker has a set command method that takes an I command. Sorry for the lack of space, but the set command method takes an I command as an argument. The I command, the interface command, has two methods. One is execute and one is unexecute. So remember, this is what we talked about with the inverse. Like execute does the thing and unexecute undoes the thing, right? Execute performs some action and unexecute unrolls that action, right? So it's like do and undo. And actually in the book they call it undo, but I just think it makes sense, kind of like as in this book, to actually talk about it as unexecute, because it's the unexecution of the execution. Anyways. And then of course any concrete command needs to implement these two. So it needs to implement execute and unexecute. And the receiver, we completely don't know, right? Because the receiver could be absolutely anything. In our case, it happens to be a light. But there's no shared interface here. So you can think about it as like, here is like an artificial boundary where this would be the same for everything. Like you have a pattern, you have a system that makes use of the command pattern. So all commands follow this particular interface. But any concrete command can have any particular concrete implementation, and that concrete implementation can sort of cross this boundary of the generalizable, all that stuff that's the same, into this very specific hard-coded land where you have any particular receiver, such as this particular light. So in the book they just put action here, just to show that the execute method of the command would probably invoke a method which performs some action on the receiver. But this completely depends on your scenario. So maybe here we would have, our receiver would be a light that has a on and off method, for example. And this is really it. This is the gist of the pattern. So let's walk through how this works. So you construct a bunch of concrete commands. Let's say turn on light and turn off light. These two have methods that are execute and unexecute. So execute of turn on a light would probably be to call on a particular light. Execute on the turn off light would probably be turn off on the particular light. And unexecute of turn on would probably be turn off. And unexecute of turn off would probably be turn on. So remember the direction of this arrow. We're saying that the invoker has many I commands. Any particular I command is a command, and any particular command can act upon a receiver. So by proxy, right, if you unroll the statement, this means that the invoker acts on receivers, right? That's the end goal. We have this thing, and we want this thing to act upon these things. But because we want to do it in a general manner, we don't want to hard code. We don't want to say that when I press this button, find this particular lamp and turn it on, right? We want to do it by proxy. We want to say that this invoker is loaded with a bunch of different commands. We refer to them as I commands. The type is I command. So we load any of these buttons with any particular concrete implementation of an I command. And that concrete implementation is a command, which follows the interface of I command. And whenever that command is executed, it performs some particular action on some particular receiver, which is completely specific to that command. Probably you can now also see how undo comes into play. So if any command has an unexecute, that means that the invoker, if it keeps track of its commands, then it can actually unexecute a whole series of commands. So this kind of makes no sense in this particular use case, but let's say that we would load one of these buttons as an undo button that unrolls every action. That means, like, let's say for 24 hours I keep track of every command that's run, and when I press the undo button I sort of unroll all of those commands in sequence. Again, like, that doesn't make any sense within this particular scenario. We'll talk about a scenario where it makes sense later on. But that would mean that I sort of play back a sequence of commands in the reverse order and with their inverse of their actions, so the opposite of their actions. So if I had a turn on command, it will act as a turn off command, because unexecute of on is to turn off. But before we talk more about undo, let's first super shortly look at some code. So I won't draw up the whole thing, but I want to draw two key portions, two key pieces. Let's look at a particular command and its corresponding interface I command, and let's look at the invoker. So what would the interface I command look like? So let's start in that end. So I command would be an interface called I command, and the only thing it specifies is that it says I have two methods, both return void, because they perform actions. If you think about command query separation, they are commands, they are not queries, but that's a totally different discussion. They return void. The first one is called execute, and the second one is called unexecute, and they take no arguments. Importantly, because the command has itself encapsulated all of the things it needs to perform its duties. The command is, going back to this idea that we talked about before, is encapsulated, right? There's an action encapsulated in a command. The command doesn't require you to pass anything to it when it wants to be executed. You've already passed all of its dependencies to it upon instantiation. So the command already has access to the receiver that it needs to have access to. In this particular case, the light. So that was I command. Let's now look at any particular command. So let's say that we're building the command for this light. So then we would have a class called command that implements the interface I command. So I'm probably going to run short on space here, but what we need is that we need a constructor. So public command. And as I was saying before, this command needs to immediately get to know about all the dependencies it needs to perform its job. So this command needs access to the light immediately. So in the constructor, we pass a light. To save space, let me just call it L. So we pass a light and then we store that internally. So we say this.light equals the L that we passed in. And then here, okay, sorry about the space, we have a light. So there's an instance variable called light. So we save away this light that's passed in into the instance variable, which we do here. That's the constructor. Then what? Then we have a method called execute. So it's a public void method called execute. Takes no arguments because it's following this particular interface. And what it does is that it acts upon the light. It acts upon its receiver. And let's pretend that this light, this receiver, has an on method. So then we would say this.light.on. Simply. That's it. It's not complex. That's not the point. It's not that we're wrapping a complex action. It could be exactly this simple. The point is not that we're encapsulating something that's complex. The point is that we're encapsulating something that's potentially trivial so that we can pass it around. If you think about functional programming, functions are first-class citizens, so it's trivial to take some procedure and wrap that in a function and then pass that function around. Command pattern kind of gives us this flexibility in object-oriented programming. So we wrap some action that we want to be able to perform, which is actually just this.light.on, right? Light.on. We have any particular instance of a light and we want to call on. So you wrap that into a class, and then if you instantiate that class, then you can suddenly pass around this object. You can suddenly pass it around as if it was a function contained in a variable. And that's the execute method. Then we would have unexecute, which is essentially the inverse of this. So we would have public void unexecute, and we would say, the implementation would be that we would say this.light.off, for example, for this particular command. But I'll just put ... here because I think you can figure that out, and then we'll close the class. And actually, of course, I called this command, but probably the name here should have been light on command, because then we would have another command, which is light off command, which has the inverse of this. So the light off command upon execute would say this.light.off. And upon unexecute would say this.light.on. So that's the light command. Let's actually add the light here. So we'll say light on command, and it's a class. Sorry about the mess. And that's that. So that's the concrete command. And key point, we might have multiple concrete commands. We might also not have multiple concrete commands. Again, We might do this even if we have a single concrete command, just so that we are able to sort of batch the execution of this command. And this is why in the book they were talking about queues, for example. Like, you might construct commands and put the commands in a queue so that you can execute them one by one or in batches, right? Like, let's say this was an expensive operation and you want to batch them. So you want to say, I have a series of commands and every 30 seconds I execute 10 of them, right? So like, you would throttle. Even if you are pushing more commands into the queue, you're sort of only taking 10 at a time every 30 seconds or something like that. Lastly, let's look at the invoker. So what would the invoker look like? So the invoker is a class, and what it does is that it somehow keeps track of commands. Remember now that this is not necessarily a part of the pattern. Actually, we could probably extend this line and say that this is really the key portion of this pattern, which might look a lot like strategy pattern, which might make you wonder, well, what's actually the difference between this and strategy pattern? And I would guess that probably the only difference is really the intent. Like, here we're treating the strategies as commands. But if you have more questions about that, please raise that as a question and then we'll dig into that some other time. So in other words, the invoker, just like the receiver, is specific to the scenario in which you're operating. It's specific to your context. Here we had lights that were receivers, right? And invoker for us was this thing. But the invoker in your scenario could be any particular thing. So actually, even in your scenario, you might have multiple invokers that have multiple different interfaces. So like, you'd have this invoker and you'd have this invoker, and then they have completely different interfaces. And in regards to this pattern, they don't necessarily need to share an ancestor. These can be concrete classes that don't share a common ancestor. They can be different classes with different interfaces, because in regards to command pattern, the only thing that they need to do is that they need to support the adding of I commands. Of course, depending on your scenario, it might make sense to share a common ancestor between these so that you could share these, so you could treat them the same way. But again, that completely depends on your scenario. If you just think about it, I mean, this control has 4 buttons, and actually, like, semantically, it's like these buttons have some kind of meaning. So like, from the user's perspective, you'd expect that these different buttons behave in sort of different ways. And this control has 1, 2, 3, 4, 5, 6, 7 buttons. So this one necessarily needs 7 commands to function properly, unless we're sort of loading one with a no command. This one necessarily needs 4 commands to operate sensibly. Again, unless we load one of the buttons with a no command. And this particular control, if you would try to load it with more than 4 commands, that wouldn't really make any sense. Similarly for this one, if you go beyond what it supports. So like, they're actually completely different things that we want to interact with in completely different ways. But the key point is that the notion of a command we make the same. So we load these things with commands, and then the commands can be shared across these different invokers, even though the invokers have completely different interfaces. Hopefully now you can actually see that makes a lot of sense, because I mean, it would be kind of sweet if this would also function as your home automation control, and this would function as your home automation control, and you could use the same software in your phone to program both of these devices or a multitude of other devices. Again, command patterns actually massively powerful. So back here, this is why we're saying that the invoker is a class and not an interface, because so far we haven't really had a need to make the invoker an interface. It's not something that needs to be shared. So let's say that the invoker concretely is this particular device. Then we have 4 buttons, and I would actually, rather than put these commands in a list, I would probably make these separate. I would probably say that this is the on button, off button, dim up and dim down, right? So let's add those as instance variables. So like, we have an I command, and actually let me just use a shorter name, I command on, and we have I command off, and we have I command, let me just say up, and I command down. And these are instance variables. So I should have expressed this in the same order as the buttons on this device for simplicity, but we now express them this way. So we have the instance variable on, which represents the on button, the instance variable off, which represents the off button, and the instance variable up, which represents the dim up button, and the instance variable down, which represents the dim down button. And as you probably noticed, the type of these instance variables is I command. Super importantly, the type is I commands because these represent what we want to do whenever that button is pressed. So in the book they use this set command method. So the invoker class has a set command method which takes a command and then puts it in one of these places. I actually think that that's a really bad idea. from this perspective. If you can avoid mutation, always try to avoid mutation. I see no reason yet for why the invoker should have to have a set command method. I would rather pass the commands through the constructor. The invoker necessarily needs 4 commands. So an invoker with 3 commands doesn't make any sense in our case. So the invoker should be instantiated, and upon instantiation we pass it 4 commands. Now, of course, I mean, you could argue that when you're building a queue, for example, you would probably want set command, because then you have, your invoker is add to queue, right? You add a command to the queue, and then you actually need to mutate the queue. Unless you have a queue that when you say add, you get a new queue back, which contains all of the old commands plus the new command. But this is a long and completely different story, and if you're interested in that discussion, I would recommend that you check out Bernhardt's talk, Boundaries, but that has nothing to do with what we're doing here. But the point here is that we can avoid the mutation, we can avoid changing the contents of the invoker as the program is running. We could rather just create new invokers whenever we need an invoker, which I would argue makes more sense, which is why we remove the set command method, and instead we just say that the invoker needs to have a constructor. So let's say public invoker. I'm just going to use 2 lines here, and it will take 4 arguments. It will take all of these 4 as arguments. So it will take, in order to save space, let me just not express the types here, but it would take an on, an off, an up, and a down. I'm not expressing the types, but this should say I command on, I command off, I command up, I command down. So the invoker takes 1 of each of these different commands that it needs. And then the implementation of this method is simply that we say this dot on equals the on that I was passed. This dot off equals the off that I was passed, and so forth for up and for down. And then we close the constructor. So whenever we instantiate the invoker, it now has access to, in this instance variable, a command that represents the on action. So whenever we say new, let's actually do that. Let's say new invoker, we pass it a bunch of commands, and for the on button, we probably want an on command, like a light on command. So then we would use this one, the light on command. So we would say new invoker, and then we pass a new light on command. And to that, we would have to pass the light, this light. And now we don't have that, but let's assume that we have a light called a light with lowercase l in the scope where we're at when we're calling this particular, when we're executing this particular line. And then we close that. So the new light on command gets past a light, because in order to be a proper command, this light on command, needs to have access to a light that it's operating on, and that light is a receiver. So we're passing that light to the light on command, and then we're taking that light on command and we're passing it to the invoker. To the invoker as its first argument, because its first argument is the on command. So then when the invoker will call execute on the on command, we will execute the light on command, which will call on the receiver, which will turn the light on. So again, by proxy, the invoker has the capability of turning this light on. And then of course up here, when we instantiate the invoker, we would have to pass the next command and the next command and the next command, 1, 2, 3, 4, which is on, off, up, and down, and then we can close that, because then we have a complete invoker. Now we haven't constructed commands for off and up and down, but I think you can see sort of how we would do that. But again, that's also the point of moving this set command, or removing this set command method and making it part of the constructor instead, because that means that it's now impossible to create an invoker which doesn't have all the commands it needs. So in order to finish this invoker code, let me just remove the interface code, because I think you can remember it, and also you can see it here. I mean, this code just represents this interface. So let's remove that, and then let's think about this. What is missing here? Well, of course, the invoker needs to be able to actually have buttons that are pressed. So probably it needs an on method, public void, and to be super explicit and to make sure that we don't confuse these with the instance variables, let's call them click on and click off, right? So if we click on, that would be a method that takes no arguments, has some implementation, and we'd have another method called, that's also a public method, returning void, and it is called click off. Should probably have called this pressed, but whatever. And then what's the implementation here, and what's the implementation here, and etc. Because now we just created the 2 methods click on and click off, but we also need to have click up and click down. But click on, super simple, would essentially just say this dot on dot execute. In other words, in this instance variable on, we have stored a command. In our example here, we happen to store the new light on command, which is past the light. So whenever we call execute on this particular on command, we will do whatever is in this execute method of that light on command. And in our case, it happened to be that the body of that method says that we will do this.light.on. In other words, that the light on command calls the method on the light that it has in its scope. And that light happened to be this light. And that's all for click on. And then the same thing we do for click off. So we would say this.off.execute. And exactly the same thing happens, but instead of that we call execute on the on command, we now call execute on the off command. So we also have an instance variable which is called off in our scope, and that off command we then call execute on that off command, which would be this command that we passed here, but we haven't actually specified what this command is, but that would be the second argument that we've passed to the invoker, because the second argument of the constructor was the off command. That's the thing that we here saved off into the instance variable called off. So we would then call execute on that, and again that would mean that we call execute on that particular command, which then would act upon some particular receiver by, for example, calling some particular action. So if we imagine it would be a light off command, and we would also pass a light, and we would pass this light, then the action would probably be to call off on this particular light. And that's it. And then we just keep on going like this. We just keep on creating invokers and stacking commands. And the key point is that, of course, at runtime, you can vary these commands. So if you're building an application, if you're actually building the app that users use to say that when I press this particular button, I want this particular series of commands to be executed, you can then give the user a bunch of different commands and then let the user choose which command should be coupled to which button, or which command should be put onto which button, so that when the user presses that button, you actually execute that command. And then 2 points. One, undoing becomes super easy because every command now has an unexecute method. And 2, you can now construct macro commands because you can now have commands that contain multiple commands. So if the command, when you call execute, if it doesn't immediately act on a receiver, but rather it has multiple commands that it calls execute upon, then that command would be like a macro command that could do multiple things. And this is one way in which you could implement the whole notion about turning on or off multiple lights instead of a single light. But before we wrap up, let's talk about this whole undo notion. So this really clicked for me when I started to think about Photoshop. Think about the image editing application Photoshop. In Photoshop, you have a long series of undo history. So you can actually you can roll backwards a super long way. And if you just think about how you would build that programmatically, it would probably not be super easy. But if you think about it this way, what if every action that you perform upon your picture, every action that you perform upon your document is a command? What if everything is a command? And what if all of these commands are rollbackable, right? What if all of these commands have execute and unexecute? What if you can do the command and then you can undo the command? And what if you then just stack all of the commands that the user performs to a document into a list? And then whenever a user wants to undo, you just do unexecute on the last command and pop it off the list. Or if you don't pop it off the list, you would just call execute again to redo, right? So you say undo, you unexecute the last command, and then you undo again, you unexecute the command after that, you undo again, you unexecute the command after that, then you redo, then you execute that last command that was unexecuted, and so forth. Then you can go back and forth in history kind of trivially. I'm not saying at all it would be trivial to build Photoshop, because the more difficult parts is of course to figure out what would actually happen in that execution. But the whole notion about doing and undoing would then be kind of trivial. And I would actually say that this is kind of an elegant way of structuring your programs. So instead of just performing some action, you wrap the action that you want to perform in some particular command, and you make sure that that particular action is undoable. So this was the command pattern. I hope that helps. Please make sure to ask in the comments if you have any sort of questions or comments, or just share your thoughts and ideas if you have something to share. It'd be massively appreciated. Beyond that, again, if you're new to design patterns, get this book. And if you want a reference book for design patterns, instead, get this book. Gang of Four, super classic book. Both links are in the description. Thank you super much for watching. Remember to subscribe, and I'll see you in the next one.